QZ3 key posted. Again, a reminder, X3 is next week. Where'd you go for exam 2? Here? Flint? I think you're in Flint again. But rather than me saying that for sure, and possibly telling you the wrong place, let me check. But I'm pretty sure it's Flint again. And I have for you a special assignment. In order to assist us in getting at chapter 23, so that you will understand what the basis for a number of important considerations that we make in chapter 23 rest on. I want you to view, study lecture 00036. You'll see that its title is Chapter 23, Analysis of Periodic Size Trends. This, of course, is where you go see this great actor playing in this famous motion picture. Winner of many Oscars. Actually, in chemistry, I think we get Erlenmeyer's. Now, you have all heard about periodic size trends in Chemistry 2045. You know, for example, or at least I trust you know, that as you go left to right across the periodic table, within an A family, like hydrogen, helium. Not within an A family, pardon me. For A family elements. Lithium on down through neon. Sodium on down through argon. What kind of size trend do you observe? Atoms get progressively smaller. And within a family, A atoms, like lithium on down through francium, but forget francium because of its radioactive nature. So we'll talk lithium down through cesium, beryllium on down through barium. What kind of size trend do we observe? Atoms get larger. Now, as you go from atom to atom, which are neighboring atoms in the same period, lithium, beryllium, you usually see a big decrease or a small decrease in size. How about lithium, sodium? Big increase, small increase in size. Big. Now, did you also realize that when it comes to size trends, you have to, practically speaking, ignore atoms which have valence d electrons, because there are aberrations in size trends. There are cases where a right side atom for transition metal atoms is larger than the left side atom, unlike the size trends which relate to A family atoms that we just talked about. So we won't pay attention to these transition metal atoms regarding size trends. But that's of no consequence, because in the main what we want to do in chapter 23 is to lay foundation for your ability, to develop your ability to understand differences in strengths of Bronsted acids. So far, we've talked about a bunch of Bronsted acids and referred to their strengths exclusively in terms of their Ka values, but have made no attempt to rationalize such. Why does this acid have a large Ka value? Why does this acid have a small Ka value? We're going to do that in chapter 23. And all of this stuff gets started with understanding periodic size trends. Now, I don't know to what level or depth these size trends were explained. Did you look at radial probability graphs? Did you talk about terms like Z effective rather than Z? And shielding? And penetration? Did you talk about those terms in 2045? Because those are the terms which are part and parcel of the language of explanation of periodic size trends for A family atoms. That's what's on this lecture. So come Monday, I'm going to believe that you will have heard all the stuff that I just mentioned, because it's in this lecture. So I'm asking that for this weekend, you find some time to take a look at this. Get out your popcorn or pizza or whatever, but no beer till after the lecture. Then come Monday, what I could do is to say, as I've done many times, put up your hand if you did this. I'm afraid to do that, because I see too many unraised hands. You know, it's quite a number of times this term when I've said in a given class near its end, here's a problem I want you to tackle, and it's your responsibility to know how to get at this when we start the next class. And just about every time I've said, okay, how many did this? I'm not seeing any responses. I want to see that with this. Do it. Between basketball games or whatever. Let's go back now and finish chapter 22. First question 22-26, which for some reason I inadvertently skipped over last time. Again, in our half reaction table, table 2 in chapter 22, you see a couple of half reactions listed which have E values but not E0 values, because the half reactions listed are not being considered to operate under standard state conditions. If, for example, you look at a half reaction which shows chemistry that depends upon hydronium ion or hydroxide ion, the only way those half reactions could have E0 values is if the hydronium ion dependent half reaction is operating at pH 0 and the hydroxide ion dependent half reaction is operating at pH 14. Any other pH is not standard state. So the couple of half reactions to which I refer are in the table shown to operate at pH 7. And again, I told you why they're included, so that you see how the strength of a reducer relates to pH of the system, and how the strength of an oxidizer depends on pH of system. Cases we talked about, because they're the cases that are considered by these half reactions. Hydrogen is a reducer, oxygen is an oxidizer. So here is the oxidation of hydrogen in the presence of water to make hydronium ion at pH 7, for which you see the E value of 0.41 volts. But again, hydronium ion, pH 7, so that can't be an E0 value. Question is, where did this value come from? How do we get it? Nothing fancy about this. Just apply Nernst. Here's Nernst. Unless told otherwise, you'll put in 1 atmosphere for the pressure of hydrogen. But what are you going to put in for this? 1.0 times 10 to minus 7. So this winds up being the log of 10 to the minus 14, which is minus 14 times a minus. So watch out, this is tough. 14 divided by 2. 7. Okay? 7 times this gives you this, doesn't it? Well, what about E0? Well, what the heck is E0 for this thing? What is it? It's 0. This is the standard hydrogen electrode, provided that it's considered at pH 0. So E0 is 0. That's all. operate on this system considering it at pH 14? Hell yes. Absolutely. But then I'd have a different half-cell reaction, but it'd be the same chemistry, except the oxidation taking place at pH 14. Now, galvanic protection. In a nutshell, here's what galvanic protection is all about. Likely you've heard about galvanic protection. Have you heard about galvanized iron or anodized aluminum? You protect the desired metal. The metal which is most commonly protected by galvanic protection is iron. Because, as I'm sure you well know, the most common metal used for construction purposes is iron. Earth's crust is abundant in iron, and it's cheap because of its abundance, and it's strong. There's, however, one problem with iron. When it's exposed to the so-called natural elements, like rain and oxygen, iron readily oxidizes to iron rust. This. Anybody yet doing any iron rust chemistry in assignment 1046L? Okay. This stuff has lousy structural integrity. And therein lies really the problem. It's not so much that iron oxidizes to this stuff, it's that when you form this on the surface of it, this stuff falls off because it has no structural integrity. And it continues then to expose fresh iron to this oxidizing atmosphere. So more iron converts to this, this falls off, iron converts to this falls off. And just as happened with my old 69 Chevelle, which I love very much because it had 300 big horses under the hood, where I used to have a fender, I wound up having a hole. That was back in the days when I was on the faculty at Santa Fe, a long time ago, in the early 80s. Every now and then, when I'd go to get in my car, because at that time there was no segregated parking, faculty here, students there. Everybody parked together. So maybe some students in the class weren't too happy because each now and then when I would go to get in my car in the late afternoon or early evening, there'd be a dent in the fender that wasn't there when I parked. Now I don't think it was because a bird bumped into the car. And after a while, dent, rust, flake, dent, rust, flake, hole. So how do we play this galvanic protection game? You take the iron you want to protect, the metal you want to protect, for example iron, and you put it in contact with a stronger reducer, a metal that's a stronger reducer, and a metal which will of course adhere to the surface of iron, or at least in some way is connected to the iron, so contact will be maintained. Perhaps some of you know that oil rig gadgetry in like the Gulf of Mexico. You know what the galvanic protection metal is used for that stuff? Magnesium. Magnesium, pretty reactive stuff, a lot more reactive than zinc. But when magnesium oxidizes, you make magnesium oxide. You think magnesium oxide is a pretty durable stuff? For example, they make fire brick from magnesium oxide. Would you like your fireplace at home to readily deteriorate? I don't think so. Magnesium oxide, that's what these bricks in the main are made from. It doesn't fall apart. Here, with the more reactive More easily oxidized zinc in contact with iron. When now the iron is exposed to the oxidizing atmosphere, you oxidize zinc rather than iron. And when you oxidize zinc, you make this stuff or this stuff, zinc rust. But these things have structural integrity. These things are stable. So they stay on the surface. You now have oxidized zinc, so it shuts down further oxidation. That's it. Chemists today are still wrestling with the problem of how to stop iron from rusting. It's an interesting and very important problem. They've concluded, with the research that's been done, and quite a lot of research has been done, that it's a kinetically controlled process rather than a thermodynamically controlled process. They've reached the conclusion, last time I looked at the results of these investigations, that it proceeds through some kind of a peroxide intermediate. So if you put a peroxide scavenger in the system or in contact with the iron, you ought to stop rusting. What they've discovered is that this slows the rusting process, but it hasn't stopped it. So they're still working on it. If you, as a practicing chemist, learn how to stop iron from rusting, if you in fact find all the details of the chemistry that's part of this process, you'd be a billionaire overnight. Just like that. That's the way the world works. General Motors might get mad as hell at you because they probably like rusting, so that every now and then you're going to buy a new car. But it's interesting, because if you work for General Motors and discover this, and they now make the cars which no longer deteriorate by rusting, then they're going to have the whole market controlled and you'll be rewarded. But watch out for Ford and Chrysler. They may attempt to assassinate you. Watch out for this stuff. Now then, the last issue wrestled with in chapter 22 is that of how to get E0 values for new half reactions. There are examples of how to combine half reactions that are in our table 2 to get a new half reaction. A half reaction, for example, which is not given in table 2. You can in fact put together a number of these half reactions and get new half reactions. But I don't see that to be particularly important at this stage of the game. All I really want you to recognize is if you get a new half reaction by the combination of 2 or more previously known half reactions, how do you get E0 for this new half reaction? You can't just add up the E0s like you do when you couple half reactions to get a net reaction. That works because now the electrons cancel. It doesn't work when you put half reactions together because you still have a net collection of electrons, either as reactants or products. There's a more detailed explanation of the why of this in the notes. But I think we'll just get at the practical aspect of this consideration, and that is, how do I get the E0 value for the new half reaction? Well, the standard method is this. You examine the half reactions which have been combined. And with the E0 value for each half reaction, you calculate its delta G0. Because the energy changes for these reactions are additive. So you operate with Hess's law on the delta G0 values in order to get delta G0 for the new half reaction. And then with delta G0 equals minus NFE0, you calculate E0 for the new half. But there's even a simpler way, which I have not yet seen considered in books. I don't know why. Go back to table 1. You remember in table at the data from table 1 we used when we were at the end of chapter 21 to show you, for example, how you could get Ka values for strong acids? Same idea. If I got a half reaction for which I don't know the E0 value, I'll just calculate delta G0 for that half reaction by use of data that's available in Table 1, and then apply delta G0 equals minus NFE0 to calculate E0. Some examples. Now, some of these half reactions may well be in our table. I don't remember which one specifically. I'm pretty sure this one's in there. But here's a half reaction where copper is oxidized to copper sulfide. Another one where copper is oxidized to copper sulfide, copper is oxidized to copper sulfide. And how about this one, where copper is oxidized to copper sulfide? So you see the obvious similarities in these 4 half reactions. 1, 2, 3, I guess we'll call this 4. Before we do any arithmetic, how will the E0 values compare? How will E0 for 1 compare to E0 for 2? Which will have, or which of these half reactions is more favorable thermodynamically? Because that's the one that's going to have the larger E0 value. Now keep in mind when I say larger, positive 0.1 is larger than minus 1. Are we understanding that? Positive 0.1 is larger than minus 1. Any plus number is larger than a minus number when you're doing this kind of stuff. How will E0 for 1 compare to E0 for 2? Which will have the larger E0 value? Which has the greater thermodynamic tendency to proceed as written? 1 versus 2. This kind of stuff I'll ask you about on exam 3. Because this is asking you to understand chemistry. In this case, chemistry of half reactions. 1 versus 2. Which got the larger E0 value? 2. Why?
Because it only has one bond.
Why? Go ahead.
You have to bring one HS bond. That's too much.
Well, for one, you're not breaking any. Well, yes, you are. Pardon me. But one point is, which you've just made, here to make sulfide ion available, so that I can make copper sulfide, I got to break one HS bond. Here I got to break 2. So that's 1 point in favor of recognizing why E0 for 2 is bigger than E0 for 1. What else?
You need less moles of water to make the reaction proceed.
These are all running water solution. You've got all kinds of moles of water. If I have a system which has HS minus at high molarity, what will be the molarity? We're looking at E0 values. What? 1 molar. Versus the other system, which got H2S at 1 molar. Which of these 2 systems is obviously more basic? This one. And what do we know about the stability of a sulfide in basic versus acidic media? Hey, the more basic the system, the more stable the sulfide, right? That doesn't mean a sulfide like copper sulfide is unstable in acidic media, but it does mean that in basic media it's got to be more stable than it is in the acidic media. By now, how many of you have marched through assignments 7 and 8 in lab? Well, what'd you find out about stuff like copper sulfide and silver sulfide? They pretty stable? You're damn right. You can hit that with all the molarity of hydronium ion you want, and you won't bring about any dissolving of consequence. All right, how about 3 versus 2? Hey, this has not only got 1 molar HS minus, it's also got 1 molar hydroxide ion. How about 3 versus 2? E03 will be, it'll be much greater than this one, right? Hey, this is at pH 14, so the copper sulfide is going to be damn stable. Well, how about 4? I'm sure 4 is not in the notes. So let's talk about right now the possibility of getting E0 for this half reaction and taking this half reaction and stuffing it into table 2. What kind of E0 value am I going to get for this half reaction compared to any of these which I've so far discussed? Four. Will E04 be greater than E01? 2. 3. No. So you already know how the E0 values for these 4 half reactions will stack up on a relative basis. Largest, next largest. And of these, this is the smallest. That's the kind of stuff you want to pay attention to before you start doing any calculation. Because if you do calculation which does not keep with this trend, which from a chemistry analysis standpoint we know must apply, if you do something with some kind of fuzzy arithmetic and you get an E0 value for 3 which is smaller than an E0 value for 2, you did something wrong. You had to. Because knowledge of the chemistry of the systems demand realization that E0 this is biggest of all the E0 values under consideration. All right? So we open up table 2. Table 1. And we see and delta G sub F super 0 for copper will be what? You don't have to look at the table for this one. It's going to be 0. Why? That's standard state copper. Well, HS minus, I got 12.1. Copper sulfide, minus 53.6. And minus 27.8. Well, let's go over here and put a 2 in front of this to account for that. That's it. Just pulling the data straight out of table 1. And now I'll apply Hess's law, and I get delta G0 for the reaction. Minus 105.6. As soon as I see this, I know that when I calculate E0 for this thing, I'm going to get a plus or minus value. Plus or minus? Plus. So, to convert my values from kilojoules to joules, I do this. Divide by 2, because N is 2 for this transformation, and the Faraday constant. Done. That's it. So we go to chapter 23. Open up your notes to chapter 23. We'll now have a very brief chit-chat about the information on the first few pages of chapter 23, because this is all stuff that you should know about. Periodic table. its breakdown. Most of the elements are metals. As you move left to right across the table, you go from most metallic to least metallic character. You think it's fair to say that argon has very little metallic character? I think that's a pretty fair statement. And interestingly enough, even though most of the metals in the periodic table are metals on the order of 80%, because all these new radioactive things that are being developed are metals, most of the chemistry that's important is centered around which elements? If at this stage of the game you are asked to identify a collection of elements upon which most important chemistry depends, what elements would you pick? Would you pick carbon? I think you should. What else? Hydrogen? What else? Oxygen. Hey, just with those three elements, you've got a whole slew of important chemistry to consider. Because you will find out in organic class that the vast majority of organic molecules are composed of those three elements. But if we want to get at the chemistry of a bunch of very important molecules, we've got to add another element. What is it? Nitrogen. Nitrogen, you betcha. And now we can get at amino acids and proteins. I think you'll agree those things are pretty important. Stuff like that. So it's interesting, we got all these elements, yet if you pay attention to H and C and N and O, you're ready to deal with a whole lot of really important chemistry. And I always have argued, at least with my students, that nature has been rather kind to us to have so much important chemistry depend upon these elements rather than elements which contain the electrons, because now the chemistry gets a lot more complicated. I mean, if silicon was the base structural atom for molecules of life, well, things would be a lot more complicated, because silicon has got d orbitals, and it makes the game more complex. But as things stand with carbon, hey, what kind of hybridization schemes in the main are we going to be concerned with when we go to organic class? What kind of hybridization are we going to be concerned with mainly in organic class? How many ways can carbon hybridize? Come on, you've done this. sp with 2p orbitals available for pi bonding, sp2 with 1p orbital available for pi bonding, or sp3 where all the bonding electrons are sigma in nature. Have you learned, have you recognized that in all carbon-containing materials which are even electron, what's that term mean, even electron? That means the sum total of valence electrons for the species in question is what? An even number. Most all stable materials are even electron species. Of the millions of known stable carbon-containing materials, damn near every one of them is even electron. And for all such materials, with the exception of carbon monoxide, carbon in its valence environment is always involved with how many valence electrons and how many bonds? How many valence electrons? How many valence electrons? 8. How many bonds? 4. Good. Now we got that part right. So if you're going to play with this whole slew of very important molecules, because carbon atom is their skeletal atom, principal skeletal atom, hey, you already got a lot on the table. You're always looking for 4 bonds, sp, sp2, or sp3 hybridization. And if you got sp hybridization, you got 2 double bonds, or 1 triple bond for the carbon atom in question. If it's sp2 hybridization, you got 2 sigma bonds and a double bond. And if it's sp3 hybridization, 4 sigma bonds. That's it. Hey, again, nature's been kind to us in that respect. Kept chemistry fairly simple. Although you may not agree with the statement, chemistry has now become fairly simple. So I'll say simpler, that's better. Okay? Now then, A atoms. Well, this whole periodic table is still constructed with the A-B labels that I prefer. A while back, International Union of Pure and Applied Chemists got together and they made a bunch of screwy family labels where you see A's applied to transition metals and all. What the hell are you people doing? That's no good. I want this. The A atoms are those which reside in the tall vertical columns. I don't know, however, why above neon in this table we haven't had the Roman symbol 8A attached. That should be there, in my opinion. Hydrogen. If you wanted to cut hydrogen, the symbol, cut it away from helium and repaste hydrogen someplace in the periodic table, where would you put it? And why would you put it there? You put it on top of lithium. Why would you put it there? Hydrogen has no chemistry at all like the 1A metals. Nothing. But why would you put hydrogen on top of lithium? Because it has a 1s1 configuration. And in that regard, you're looking at what I consider to be the most important periodic property of any atom. Its valence electron configuration. 1s1, 2s1, 3s1, 4s1, down the line we go. What are you going to do with helium? Well, property-wise, you're going to put helium on top of neon. No question about that. But electronically, where are you going to put helium? On top of beryllium. Great. 1s2, 2s2, 3s2, and on down we go. All right. Notice on page 23.4, there's a table 3, which gives you the ground state electron configuration of all the atoms of the elements. So that, if it need be that you get at the valence electron configuration for an atom, then you don't remember how to do it, or you remember what it is, there it is. But you don't know how to play this game. You learn this in 2045. You learn, for example, that one of the characteristics of A family atoms is that they all have the same type of valence electron configuration. This is what we were just talking about. All S1 for 1A, S2 for 2A, and stuff like that. But you got to be careful. I mean, you got to remember that when you go to these transition metals, then this game doesn't apply. For example, when you played with this so-called Aufbau order, remember that in 2045? You learned that with the Aufbau order, you could write the correct ground state electron configurations for all atoms up to and including zirconium number 40 by application of Aufbau, with 2 exceptions encountered along the way. What are the 2 exceptions? Chromium and copper. So you wrote for chromium, which is number 24. Argon, which immediately represents 18 core electrons for chromium. Now you got to put in 6 more electrons. And you're remembering this Aufbau thing. And the Aufbau thing showed you that from a relative energy standpoint, the next electrons added in developing this configuration go where? What sublevel? 4s or 3d? Where do they go? 4s or 3d? Well, let's go back to potassium, which is the first atomic member of period number 4. Because potassium is argon core, what? 4s1. And calcium is argon core 4s2. And you never get a d electron in any configuration until you finally get to scandium, number 21, which is 4s1, 3d1. Well, let's back this off to scandium. I've now written the configuration for scandium, total configuration for scandium, in accord with the Aufbau order. But I'm curious now about, for example, this species. Because to make this species, I apply to scandium its first ionization energy. So I get out my ionizing cannon and I go, bam! I want to know which electron goes away, because I'm remembering that this was the last electron I added. So if the order of removing electrons to develop positive ions is anti-parallel to the order in which they were added, then scandium plus would be 4s2 3d0, wouldn't it? Is that what scandium plus is? No. So I'm going to take this configuration and rewrite it. I'm rewriting it on the basis that when I subject an atom to ionization, the highest n-value electrons always go first, to which there is no known exception. So scandium single plus is argon 3d1 4s1. And scandium double plus is 3d1. And I don't take away that 3d electron until I create scandium triple plus. And then, as I proceed further, I get to chromium. So we'll comment on chromium, and we'll stop there. Here's chromium, based on Aufbau. But I take chromium and I subject it to measurements of paramagnetic character. Remember that? For our purposes, in the main, paramagnetic character measurements give us a way to get a handle on true ground state valence electron configurations. Because when I investigate chromium ground state, I find out that its valence electron configuration has how many half-filled orbitals? 6. How about that? Because true chromium ground state is this. Each of the 5 orbitals in the 3D sublevel are half-filled, and the 4s orbital is half-filled. How about that? So that accounts for my first exception. But by paramagnetic character measurement, I can find out this is correct, but not this. Because if this was correct, how many half-filled orbitals would I have? 4. Right? Difference in paramagnetic character. And I play this game, again, when I get to copper. But I see a problem. Here's copper. But Aufbau would predict and they say, what do I do now? Because the correct configuration is this. How many half-filled orbitals? But Aufbau predict is this. How many half-filled orbitals? How many? How do I tell them apart? Ha! Now I have to realize that if I make my paramagnetic character measurements in a very careful and precise fashion, I find out that the paramagnetic character of an electron in a 4s orbital is different from the paramagnetic character of an electron in a 3d orbital. How about that? But at this stage of the game, we don't have the wherewithal to make paramagnetic character measurements, so we're not going to be responsible for that. We'll pick it up from this point next time. You do this.